Hello class, in this video we'll be using stoichiometry to determine the heat energy released from the combustion reaction as well as the volume occupied by a greenhouse gas from its thermochemical equation. When we last looked at thermochemical equations, I've mentioned that the coefficients of the thermochemical equation states the number of moles of reactants needed to give off said enthalpy change or heat released. For example, if we were to interpret the thermochemical equation for the combustion of ethane down below, this states that 2 moles of ethane undergoing combustion would release 3,120 kilojoules of energy. In the first section of this video, I'm going to first show you how we could use stoichiometry to find out what is the amount of energy released for a specific amount of fuel. Let's take a look at an example. In this example, we want to calculate the heat energy released in megajoules when 10 kilograms of octane undergoes complete combustion and we're provided with the thermochemical equation. Based on this equation, we know that 2 moles of octane releases 10,900 kilojoules of energy. In order for us to do mole ratios, we need to calculate the number of moles of octane. To do this, I'm going to first convert kilograms into grams because this is the standard units for mass, and if we divide this mass with its molar mass, I can find the number of moles of octane. Based on our calculations, this suggests that 10 kilograms of octane is equivalent to 87.7 moles. The next step is for us to calculate how much energy is released from 87.7 moles. So what we could do is we could use mole ratios and we could set up the mole ratios in the following format. In this example, the known amounts are derived from the thermochemical equation. Hence, I could place 2 moles of octane here and this releases 10,900 kilojoules of energy. The unknown part of this setup is related to what you are actually trying to find out based on the data given to you. So if you plug this in correctly, this is how your ratio should look like. This ratio is saying that the energy released from 2 moles of octane should be proportional to the amount of energy released from 87.7 moles of octane. To solve for Q, we multiply both sides of the equation by 10,900, and if we enter these values into the calculator, you're going to get an answer of 4.78 times 10 to the power of 5 kilojoules. This value indicates the amount of heat energy released by 10 kilograms of octane. However, because the question wants us to express this value in megajoules, we can do this by dividing our answer by 1000, giving us a final answer of 478 megajoules. I would now like you to attempt a similar question. Pause the video now and resume the video again when you're ready to compare answers. In this question, we want to find the heat energy released from 10 kilojoules of ethane. To start off, I've converted 10 kilograms into grams by multiplying 10 by 1000, and I proceeded to calculate the number of moles of ethane by dividing 10,000 with the molar mass of ethane, giving me an answer of 333 moles. Using mole ratios, we should now be able to generate the following equation based on the stoichiometric amounts in the thermochemical equation. To solve for Q, we multiply the equation by 3,120, and this will give us an answer of 5.2 times 10 to the power of 5 kilojoules. Lastly, we need to express our answer in megajoules by dividing our answer by 1000, giving us an answer of 520 megajoules. In the next section of this video, we're going to be looking at a slightly different example that involves calculating the volume of greenhouse gas. In this example, we want to calculate the volume of methane, which is a greenhouse gas required to produce 4 times 10 to the power of 4 kilojoules. Because this is measured under standard laboratory conditions, we could use the formula V equals to N times Vm to calculate volume. However, because I don't have the value of N, I could do this by performing mole ratios. This ratio pretty much says that X amounts of methane produces 4 times 10 to the power of 4 kilojoules, whereas 1 mole of methane produces 890 kilojoules based on the thermochemical equation. To solve for X, we're going to divide these two numbers together, and this should give us an answer of 44.9 moles. Now, we could use this formula over here where Vm equals to 24.8 under standard laboratory conditions, and plugging these numbers into the calculator will give us an answer equal to 1.11 times 10 to the power of 3 liters. It's your turn to have a crack. Give yourself a minute or so and then play the video again when you're ready to review your answer. We're going to begin this question by using mole ratios to find the number of moles that releases 5 times 10 to the power of 3 kilojoules, given that 1 mole of methane releases 890 kilojoules. We solve for X by dividing these two numbers, giving us an answer of 5.62 moles. By multiplying the number of moles of methane with the molar volume at SLC, we're going to get our final answer of 139 liters, which is the volume of methane required to release 5 times 10 to the power of 3 kilojoules of energy. By now, you should be able to meet the success criteria in this video. If you found this video helpful, please give it a like. Thank you for watching, and I'll see you guys again in the next one. Bye.